Join with computer audio. All right. Let's see my chat. Okay. We need a couple of clicker problems. And why? No. What's this one? Found crash recovery. No. Are we out again? Are we really out again? Hold on, I'm gonna call him. I'm gonna call. Just wait, he's gonna come bring some in just a second. So I don't want you to, people were sitting at y'all desk. I want y'all to have that. Like they couldn't put the, I know, I'm calling right now. I'm calling right now. If y'all want to grab a one from over there. Whoa, that was really weird. When you check in at the front, they always have extra. So we can borrow from there until, let me try this. Okay, where did we end up on clicker question? CANS. Hey, Andre, this is Dr. Sarah Bajra. I'm in the ballroom in the Union. We are out of sanitizing wipes again. I tried your cell phone, but I couldn't leave a message there. So I'll try it again one more time. Thanks. Bye. Did they have some over there? Thank you. Hey, Andre. This is Dr. Sarah Bajra in the room 19, the ballroom. Unfortunately, we're out of wipes again. Okay, I appreciate it. Thanks. Bye. Okay. All right. So where were we? Were here. What time is it? Ooh, it's time to start. Okay, so we're starting off. I want to tell you a few things because I need to also do attendance. That's what happens when I get distracted. I know I have attendance here somewhere. Here we go. Okay. So tell me if you are present in the classroom or remote at home. Thank you. No, I'm good. Who has me? Thank you. Thank you so much. Okay. All right, so do your attendance. me turn on my mic. Okay, is that better? Do your attendance. Okay. I'm going to minimize this. There are a couple of things I wanted to tell y'all. I would like to close this. Okay. A couple of people have asked, oh my goodness, here we go. Have asked for some additional videos and things like that for this chapter. And so I don't know if I told y'all, but I thought I did, but maybe I didn't. If you come down here to our Unit 2, Chapters 3 through 5, so this is the material we're working on right now. If you come here, lecture slides, in-class problems, and video links, and you scroll down, those are my videos. Those are my videos. But then at the very bottom, it says Chapter 3 Extra Video Resources. These are not required, and they're not. But some people wanted just extra, seeing somebody do some of the problems, that kind of stuff. And so I've organized it by section. So there are a lot of different videos, whatever you're struggling with. Hopefully there's something here for you. If you're struggling with something and I don't have a supplemental video and you would like one, please send me an email. I'll try to see what I can do. Okay? And you can always set up a Zoom with me if you need some help. So close that. Okay. And then y'all know where to go to set up a Zoom? Right here on the main page, it says appointment calendar. That's like my office hours. Okay, because I know we all have to social distance, but make a Zoom appointment with me. I'll help you. Okay. See if I can close this stuff. All right, so we're going to start out with a couple of quick clicker questions. So everybody has done your attendance. Please do your attendance if you have not done your attendance. I'm telling you that you're going to need a periodic table in order to do these clicker questions. So make sure you have a periodic table and you have a calculator ready to go. Okay, so I'm assuming everybody's got attendance. So this is the one we did last time, right? CA-NO32. Okay, what is the formula unit for sodium phosphate? What is the formula unit for sodium phosphate? Oh no, I think we didn't do that other one. That's okay. It's okay. I'll give you about a minute and a half. Write it down. Okay, 10 seconds. Okay, so what should you have gotten? You should have gotten E. You should have gotten E, so let's talk about that. So if you're sodium, what column are you in the periodic table? What group? You're in group 1A, right? So you're a cation, you have a charge of +1. You had to recognize that that PO4 is a polyatomic ion. Where can you go get information about polyatomic ions? On the table in your notes, it's also in the book, and I did you a favor. And I also put it over here. Where did I put it? Here we go. So for your exam 2, you'll have the periodic table, you'll have the names of the elements, the equations, the conversions, and the polyatomic ions. So if you forgot to bring one, you don't know where to go get one, scroll down, look, here they are. Okay, so you have this as a resource on your exam. Let me go back. How do I go back? Here we go. Full screen. Come on. Okay. So you should have gone to your polyatomic ion table and you should have gotten PO4 3 minus. So be careful that that's phosphate, ATE, tells you it's PO4. Okay. Now you take your charges and you do the crossover. So the 1 on the sodium goes down here for a subscript on the PO4. The charge on the phosphate comes down and becomes a 3 for the Na for the sodium. So you should get Na3PO4. Okay. Let's try another one. Now be careful with this one, something's changed. Select the incorrect name formula pair. So which one of these is not the correct formula for the name? I'll give y'all a minute and a half because you're looking at a bunch of different ones. Okay, 3 seconds. Go ahead and ring in if you have not rung in. Okay, so what should you have gotten? You should have gotten that the incorrect one was sulfur dioxide and SO3. What does di mean? 2. But what are you, how many oxygen atoms do you have? 3. Now, what's the difference between all of these compounds that are listed here and what we did here? These compounds listed here. These are one kind of compound, and these are another. These are covalent, and these are ionic. How did you know that? We always have a metal and a non-metal, or a metal and a polyatomic ion, right? Whereas here, what do we have? Carbon is a non-metal, oxygen, non-metal, 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 right? Okay, now let's see if you can apply that. Which compound is ionic? Which compound is ionic? Give it to 1 minute. And that's 1 minute. So if you have not rung in, ring in. And keep until 1 said, ring in. Or not paying attention. I think we had 47, right? Okay. So which compound is not ionic? And the Ca, which is ionic, not what is not. Yeah, what is ionic. So calcium is what? A metal. If you only have to look at the first element to know if it's ionic or covalent, right? Carbon's non-metal, nitrogen non-metal, sulfur non-metal, oxygen non-metal. The only one that had a metal to start out with was C. So there are only 3 ways that you can have an ionic compound: a metal and a non-metal, a metal and a polyatomic ion, or a polyatomic ion and a polyatomic ion. Okay? All right, let's see. Okay, we'll do, let's see where we are. We'll do 1 more. Okay? How many dots are in the Lewis dot structure for a bromine atom? Ooh, I have to start a new one. You shouldn't have to take a minute for this one. Okay, you have not run in, you got about 5 seconds. Okay, so what did we say? How many are in the Lewis dot diagram for bromine? Bromine's in group 7A, so you should have 7 valence electrons. And if you're going to do an electron dot diagram, right, we do them all individually and then we pair them up, right? Okay, so let's switch gears and let's go back to our in-class problems. If I can figure out how to do that. Here we go. Okay. Where did we left off? I think on 3.32. Is that right? 3.32. I think this is where we were. It didn't save our work, but I think we were on the very last one. I think we were on D. Is that right? Oh, feeling pretty good. Okay. Use full screen. Okay. So I want C2H2. I'm going to draw the Lewis dot structure. So let's do it, not the needed available shared method. Let's do the just valence electron method. So what's going to be my central atoms? Carbon or hydrogen? Hydrogen cannot be a central atom. It only has 1 valence electron, so it just doesn't have enough electrons to bond to more than one thing. So carbon's always going to be our central atoms. And then we have 2 hydrogens. So we'll put them kind of flanking our carbons. So how many valence electrons in carbon? Not 6. Look at your group. You have 4. So you're in group 14 or group 4A. And so you have 4 valence electrons. All right. I like to give hydrogen its duet first. So how can we do that? How can we make sure hydrogen's happy? Good morning, y'all. It's not even morning, it's afternoon. What am I talking about? It's the afternoon. So we want to give it some bonds, right? So in order to give hydrogen an octet, all we need to do is make 1 bond, right? So that means we're going to share those 2 electrons between the hydrogen and the carbon. So when I count around hydrogen, hydrogen now has 2 electrons. I'm going to do the same thing for my other hydrogen. I'm going to turn those two individual electrons into a shared bond. We okay on that? Now, are my carbons happy? Oh, they're not even bonded to anything yet. So let's give them a single bond and let's see what happens. So now is carbon happy? No, I got 2, 4, 5, 6. That doesn't cut it. I need 8. What am I going to do? I need to turn these into another bond. I need one electron from each atom to make a bond. Are the carbons happy? Not yet. They only have 7 electrons right now, each of them. So I'm going to make another bond. And then, because that really looks ugly, I'm going to rewrite it. Are my carbons happy? Yes, they have 8. So I have 2, 4, 6, 8. I have 2, 4, 6, 8. Both of my carbons are happy. So that is a good structure. Okay. All these chords, it just gets ridiculous over here. All right, now this should be pretty easy because of our clicker questions, right? Determine whether each of the following is a covalent or ionic compound. So I'm going to look at that first element and I'm going to say, is it a metal or is it a non-metal? So K2O, my first element's K, potassium, metal or non-metal? Metal, so what kind of a compound? Ionic. CO2, metal or non-metal? Carbon. Non-metal, so it must be covalent. Y'all see that? Y'all see how I can go through these pretty quickly? I don't actually have to identify the second element. All I have to do is look at that first element. The only time that that's not true is if that first element is part of a polyatomic ion. Then you have to be careful with that one. Okay, C, ionic or covalent? Ga, where is Ga? Ga is number 31. It is ionic because it is a metal. It's a transition metal, but it's still a metal. C2H6, ionic or covalent? Covalent because carbon is a non-metal. NiCl2, ionic or covalent? Nickel is number 28. Ionic, nickel is a transition metal. BaSO4. Ba is number 56. That has to be ionic. Barium is a metal. SO2. Covalent. N2O. Covalent. NH4Cl. Be careful. It's ionic. How did you know it was ionic? NH4 is a polyatomic ion. So remember our little rule. If you have a non-metal plus, I'm sorry, like Dr. B can't think today. If you have a metal plus a non-metal, a metal plus a polyatomic, right? A polyatomic plus a polyatomic, right? If you have that polyatomic to start with, it can be an ionic compound. So ionic. NH4 is the only positively charged polyatomic ion that I think y'all are going to deal with. All right, SiH4. Ionic or covalent? Si is number 14. Now be careful with this. What color is it? It's a weird color, isn't it? Doesn't matter which periodic table you're looking at. Right here. Why is it green? It's a metalloid. So they have properties of both a non-metal and a metal. That's why it's on this like little staircase, right? So we classify these as covalent. Okay. So those were your two tricky ones. The last two were your tricky ones. Remember, I try to trick you in class, so I can't trick you on the exam. The whole point. Oh, and y'all caught, a bunch of y'all caught my error. I had 2 errors in my videos for this chapter so far. I'm so sorry. So I was trying to name this compound right here, H2O. Like, come on. I named it dinitrogen monoxide. Is that right? No, that's not right. What should it be? Dihydrogen monoxide. But I really want y'all to go around telling people, oh, I have this nice glass of dihydrogen monoxide. It's so delicious, right? Do you know how much you're going to freak people out? But what are you saying? Well, I had a nice drink of water, right? You know? The next time you go out to a restaurant, you know, can I have some dihydrogen monoxide, please? Just for the looks on their faces. Okay. All right, now we have something we actually have to name. N2O4. How do we know how to name this? Is this an ionic compound? N2O4, ionic or covalent? It's covalent because nitrogen is a non-metal. So what do we have to do? What were our naming rules? Remind me of that. Prefixes for subscripts. Anything else? We're going to end in "ide." Okay, that's my shorthand for my rules. So N2O4, what is 2? What's our prefix for 2? Di. Oh, here's my nitrogen finally, right? Dinitrogen. I can't speak and spell. It's really terrible. I have to like pause to spell. Dinitrogen, what is 4? Tetra. But we don't put the A because putting an A and an O next to each other, it's really hard to pronounce. So we just say it tetroxide. But I would never take off points on an exam if you put an A. Like, I know some people who are like that, and I'm not like that. I'll never take off on spelling. That would be too hypocritical of me, way too hypocritical. All right, so carbon monoxide. Why don't I have a prefix here? Because there's only one, and it's the first element. And so if you only have one of that first element, you don't have to put anything at all. Okay, so that's telling me I only have one carbon, and then how many oxygens? I have oxide, so that must be oxygen. I only have one, CO. All right, P2O5. 2 we said was di. What is P? Phosphorus. PHOS. PHOUS, phosphorus. And then what's 5? Pent, and it's penta, but we drop the A, oxide. Okay, carbon dioxide. How many carbons? Only one again. Di meaning 2, and we have oxide, IDE is on the periodic table, so it's just 2 oxygens. Okay, NH3. How do we say that one? Nitrogen trihydride. Nitrogen trihydride. Anybody know the common term for this one? Ammonia. This one's ammonia. Peroxide is one though, H2O2. So that does have another name as well. There are a lot of molecules that are like that. They have a common name and then they have a scientific name. All right. Y'all ready to do some more dimensional analysis? Yo, like, she's so crazy. She's just excited about dimensional analysis. Okay, so remember when I said dimensional analysis wasn't going away? It's really not going away. You got to get on board. If we didn't get you on board before, you got to get on board now. Okay, whenever you're reading a problem like this, we have to think about what we're starting with, what's our goal, and what are some conversion factors we need to get there, right? Okay, so 3.38, compare the number of atoms and the number of grams present in 1 mole of a helium and 1 mole of argon. So let's do the atoms first. So is this what I'm starting with or my goal? Number of atoms. That's my goal. What am I starting with? 1 mole of helium. Be careful that you know not only the normal unit that we've talked about, but that you also know what element or what compound it is, because that's going to be super important later. So I'm going to start with 1.00 moles of helium. I'm trying to get to atoms. I know moles is going to have to go on the bottom, so I'm going to put moles of helium on the bottom. Can I go straight to atoms? Yes, we can. Yes, we can. Yes, we can. We know Avogadro's number, right? 6.02 times 10 to the 23rd, right? Really big number. Think really, really big number. Times 10 to the 23rd. Things in a mole of things. Like you could have a dozen M&Ms, right? Or you could have a mole of M&Ms. If you had a dozen M&Ms, how many M&Ms do you have? Only 12. I'm not sharing. I'm not sharing. If I got 12, that's my 12. Now, what if I had a mole of M&Ms? I would share with everybody, right? We would almost fill up the earth with that many M&Ms. So that's definitely a sharing bag size, right? The mole size. So remember that Avogadro's number is like a dozen. You can have a dozen of anything. You can have an Avogadro's number of anything, okay? So we have 6.02 times 10 to the 23rd. In this case, what's our thing gonna be? Atoms of helium in a mole of helium. I like this math, right? How many atoms we got? Atoms of helium. My moles canceled, right? So we didn't really have to do that conversion factor, but it proves a point. You're not always going to start out with 1 mole. How about if I have 1 mole of argon? I know I'm going to have 1 mole at the bottom. Not helium, argon. How many atoms in 1 mole? Same thing, 6.02 times 10 to the 23rd atoms of argon. So what's my answer? So does it matter if you start with a mole of helium, or you start with a mole of argon, or you start with a mole of M&Ms? How many atoms are you going to have at the end? 6.02 times 10 to the 23rd. You know, a mole of M&Ms sounds good on the outside, but when you actually think about how many it is, I don't want a mole of M&Ms. I don't. But a mole of other things is not so much. So I did not put the right amount of room, so I'm just going to erase. Oh, it said compare. Wait, it said compare. So what do we say? What's our comparison? They are what? The same. Make sure you answer the question that is asked. I would take off on an exam for that. Okay, so we're going to do part B, right? Okay, part B. Now we're going to compare the number of grams. This is my new goal. But I'm starting with the same amount of material. So I'm starting with 1 mole of helium, and I'm starting with 1, it's really 0.00 moles of argon. How am I going to convert from moles to grams? I need to go to the periodic table, right? Because on the periodic table, in each of those little squares, you have 2 pieces of information, right? You have the atomic number, which is the number of protons, and then you have the atomic mass. So that number right there, 4.003, that is the number of grams of helium in 1 mole of helium. Okay, so I can say in 1 mole of helium, I don't know why it came out like that, it's not 7, it is 1. In 1 mole of helium, I have 4.003 grams of helium. So our moles cancel. What do we get? We have 4.003 grams of helium in 1 mole of helium. How about argon? I don't quite need to go that far. In 1 mole of argon, how many grams do I have? Go find it on the periodic table. 39.95 grams. So my moles cancel. I end up with 39.95 grams of argon. Are my answers the same now? No, they're not. Let's talk about this for a second. Does it make sense that they're not the same? And it absolutely does. What takes up mass inside of an atom? Protons and neutrons. So if I look at helium, do I know how many protons and neutrons I have? I know that I have 2 protons, and I'm not given a mass number, but most isotopes of elements have the same number of protons as neutrons. The isotopes are the ones that have a different number of neutrons, right? So most of the time, you're going to have the same number of protons as neutrons. So what would be my mass number for helium? Approximately. If I tell you you have equal numbers of protons and neutrons. 4. Oh, what's your atomic mass of helium? 4.003. Huh, pretty close, right? Okay, argon. Argon has 18 protons, right? That's the atomic number. So let's say the most common isotope also has 18 neutrons. What's going to be the mass number for argon? 18 plus 18 is 36. My mass is 39.95. That means I have some isotopes with more neutrons. But how close was that? Pretty close. And the reason is because the things that take up mass inside of an atom are protons and neutrons. So the more protons and neutrons you are, the heavier your atom is. So does it make sense that helium is kind of a light element, whereas argon's kind of a heavy element? Yeah, argon's got more protons and neutrons than helium. So you're going to have more grams of argon in 1 mole than helium. Yeah? I think a lot of people miss that connection, right? So if you just think about what takes up mass, that'll make sense. Okay, and so they're not the same, and they depend on the mass of the individual atoms. So they are not the same. Let's write that. Not the same. So the greater the mass of the element, the greater the mass of 1 mole, right? Because like this is how I kind of think about it too. I'm on the M&M thing, you'll have to forgive me, right? If you took a peanut M&M and a plain M&M, do they have the same mass? No, which one's gonna be heavier? A peanut M&M. So if I had a mole of peanut M&Ms and I had a mole of plain M&Ms, which one's gonna have more mass? My peanut M&Ms are gonna have more mass because each individual peanut M&M weighs more than an individual plain M&M. Yeah? Okay. All right, I'll stop talking about M&Ms. It's gonna make me want. All right. Calculate the following: the number of sulfur atoms in 0.660 moles. So now I'm not starting out with a whole mole. I'm saying I only have a fraction of a mole. So am I going to have 6.02 times 10 to the 23rd atoms? No. Can you tell me, do you think you're going to have more or less than 6.02 times 10 to the 23rd? If I don't quite have a whole mole, am I going to quite have 6.02 times 10 to the 23rd? No, so it's going to be a little bit what? Less, a little bit less. So let's see if that math works out. Let's see if our intuition is correct. So we're going to start with 0.660 moles. Okay. I know I want moles on the bottom. And I know I want to get to atoms. So what relationship, what conversion factor do I know? I have 6.02 times 10 to the 23rd atoms of sulfur and 1 mole of sulfur. Okay, so put the math in your calculator. What do you get? $3.97. Careful. Times 10 to the 23rd atoms of sulfur. So how much less do we have? Half of 6 is about 3, right? So we have a little more than half of what we were expecting. Is that right? Yeah, because instead of being a mole, we're a little bit more than half of a mole. So this is a little bit more than half of Avogadro's number. Makes perfect sense. Now this one's not quite so intuitive, B. I'm starting out with 15 grams of iron. I want to know how many moles that is. 15 grams, that's not a lot, right? 15 grams, 12 grams is like 2 batteries. So like 2 AAA batteries and a little bit more. That's not a whole lot. So how do we do that? How do we go from grams of iron, and I want to get to moles? I'm going to go to the periodic table and I'm going to pull my atomic mass. So I have 55.85 grams of iron in 1 mole of iron. So what do we have? I'm going to do the math. grams cancel, we're left with moles. So 0.269, that's still kind of a lot. So what do you think about it, the atom size? Compared to an M&M, look, I went back to M&Ms, I'm sorry. Compared to the size of an M&M, what's the size of an atom? Like so tiny, right? So tiny. I don't even want 0.269 moles of M&Ms. I don't even want that many M&Ms. That's too many. Okay, let's see if I can extend the page. I keep just writing on the page. Okay, so my next one, number of atoms in 66 grams of copper. So I have 66.0 grams of copper, and I want to get to number of atoms. Can I go straight from grams to atoms? Do I have a conversion factor for that? No, but we got to go to one of my favorite places. Do you want to know one of my favorite places? Mole Town. It's like the coolest place ever because you can go from grams to atoms. You do all kind of conversions if you just go to Mole Town. I had somebody even draw in one of my classes one time. They drew me Mole Town, and it was pretty awesome. All right, so what's our relationship between moles of copper and grams of copper? So I know in 1 mole, I got to come up here. I have to look here at my atomic mass, and I have 63.55 grams of copper. So am I done? Nope. Always go back up and look and say, okay, I'm looking for number of atoms, but I'm only in moles. So that's not where I want to go. I got to go again. What do I know about the relationship between moles and atoms? I know, Avogadro's number, 6.02 times 10 to the 23rd atoms of copper in a mole of copper. So our moles cancel. We're left with atoms, and that's what we want. So it should be a pretty big number. What do you get? A lot of atoms. That's a lot of atoms. It's a huge number. We write it in that scientific notation and we don't think about it, right? But it's huge. Okay, let's see. Let's go to the next page. All right, and I made a mistake here on the video. Here, this one, right here. I made a mistake. I didn't add correctly. The correct answer should have been 180.16. So everything in the math, everything in the problem is correct. I just apparently didn't put it in my calculator right. Okay. So a couple of people caught it. So good job, y'all. And always let me know when I make a mistake. It will happen. It will happen. Okay. Determine the molar mass for the following compounds. So how do we determine the molar mass of anything? What is a molar mass? So when we talk about a compound, right, you're talking about multiple elements and then multiple atoms of all of those elements. So in order to know the mass of the entire compound, and we express that always in grams per mole, we're going to have to look at how many of each element we have and the atomic mass of those elements. So let's start with carbon. How many carbon atoms do I have? 2. And so I'm going to go look on the periodic table. I'm going to find carbon. I just like drew on it. All right. I find carbon, and carbon has how many grams per mole in just carbon? 12.01. And you can leave the units on here if you want, or you can leave them off. Doesn't matter.
plus my hydrogen. How many hydrogen atoms do I have? I have 4 hydrogen atoms. And what is my, here, atomic mass for hydrogen? Times 1.008 grams per mole. So if I add these up, I should get my molar mass for my compound. So what should my molar mass of my compound be? And my units, whoa, I started typing. How do I delete that? So embarrassing. Oh, what did I do? Let's see, no, that's the next page. The D's are probably still there. They are indeed. Oh, there we go. All right. Okay, what are my units? It's always grams per mole, but in this case, it's not just carbon, it's not just hydrogen, it's grams per mole of C2H4. So it's for the whole molecule. So this is why it's important, like I said before, to make sure to write after the unit, is that the atom, is that a molecule? Like what, you have that many moles of what, or that many grams per mole of what? So be very careful about that. Okay, B, citric acid, C6H8O7. So my carbon, I have 6, and we already said that carbon was 12.01. My hydrogen is 8. We already said that hydrogen was 1.008. And oxygen, if we scroll up, we'll find oxygen right here. Oxygen is 16. So what is my molar mass for my entire compound? I got 192.12. Is that what y'all got? All right. So which one between A and B, which one do you think is a bigger molecule? The second one. It's got a bigger molar mass, right? So that makes perfect sense. Good job, y'all. All right, I'm going to erase A to fit in C. I promise when I was making the next chapters in class problems, I put lots of space. So hopefully the next one will be better. So NaHCO3. So we have 1 of sodium. Did I put sodium here? Oh, I did. Sodium is 22.99. Plus I have 1 hydrogen, which is 1.008. I have 1 carbon, which is 12.01. Ooh, I'm still running out of room. Plus, I have 3 oxygen, and we said that was 16.00. So what I got was 84.01 grams per mole. Yay or nay? Is that what y'all got? All right. We've already established I make calculator errors. So always check my math. Happens to the best of us. Okay, now, let's see if I can extend the page. Oh, there we go. Okay. Now we need to determine, uh-oh, is my mic off? Yeah, I bet it died. Low battery. Hang on. We're supposed to have batteries. Sorry, y'all.
Okay, try 3.44 without me. Try it while I try to get this open. Come on. It's supposed to just pop open. There we go.
Okay, is that better? Yeah. Okay, so what are we starting with? 200 milligrams of ibuprofen. That's a common pain reliever. O2, an anti-inflammatory. Okay, so what did you automatically send up a red flag? Oh my goodness, I need to do something. What did you see? We saw milligrams, and we know that there's no conversion between milligrams and anything else. So you should see that milligram and go, whoa, hold the horses. Can't do it, right? So first things first, I want to convert out of milligrams. I know I have 1,000 milligrams in 1 gram. A milligram is tiny. Now I am in grams. I'm still in grams of C13H18O2. All I did was convert the milligram to gram. And I want to get to what? My goal is to get to number of molecules. So guess where we're going? Oh yeah, we're going to Mole Town. All right, so how do we get to Mole Town? I want grams of C13H18O2. And I want to go to moles of C13H18O2. How am I going to do it? I need to calculate my molar mass. So I know in 1 mole, I have my molar mass, but how do I figure out my molar mass? I'm gonna have to do the calculation. So 13 times 12.01 is my molar mass of carbon, plus 18 times 1.008 is my molar mass of hydrogen, plus 2 times my molar mass of oxygen, which is 16. When you do this enough, you'll know some of these without having to look. And I guess I'll just put the, it's gonna be right there. So what's our mass? I love the sound of calculators. It's like music to my ears. Maybe that's the soundtrack to Mole Town. At least I'm entertainment for y'all. Okay, so what do you get? I got 206.274. So the other thing I want to say while we're doing this is, should I be rounding in the middle of all my calculations? No. Why not? Where should I round? At the very end. Okay, good. So are we where we want to go? Still not where we want to go. Now we got to leave Mole Town. All right. So let's leave Mole Town. Put moles on the bottom. C13H18O2. So if I leave Mole Town, I'm trying to get to molecules. How do I get to molecules? I know my Avogadro's number, right? So it's 6.02 times 10 to the 23rd of anything, but in this case, we're going to say molecules of C13H18, I'm running out of room, O2. So when you put all of that into your calculators, I'll give you a second. What do you get? molecules of C13H18O2. That's a 3. My wrist keeps hitting things. How about significant figures? I'll tell you, your book made a mistake. They said it's 200 milligram dose. Do you really think that that's only one significant figure when you prescribe something? No, really what they should have done was a 200 decimal place milligram dose. But everyone makes mistakes, right? So we're going to assume 3 significant figures. So we're good. But if we didn't do that, how many significant figures? And it was really what they have in the question. That's 1 significant figure. So just be careful about that. Okay, now we're going to move on, right? New topic. Done with dimensional analysis. Woohoo! Well, at least for this chapter. It never really leaves. I laugh, but I don't think y'all are laughing. I'm sorry. I could tell you my son's joke of the day. Y'all know, so I give my son a joke in his lunch kit every day. I print them. I don't come up with them. I print them. But I'm still pretty proud of myself for doing it. So today it was, what is a duck's favorite snack? Cheese and quackers. They're all like that. They're all terrible. All terrible. But anyway, okay. Now we're going to start thinking about these molecules that we're building in 3 dimensions. Everything we've done so far, we've drawn on the sheet of paper, right? And a sheet of paper is not real life. Real life is 3-dimensional. So we have to figure out some way to still write our answers on paper, but express it in 3 dimensions. So when we write on the paper, when you graph something, how many axes do you use? Use 2. Typically you use 2, right? X and Y. Now, what's the 3rd axis? I wish I had a 3rd arm. It'd be cool. There's another axis. It's not here. It's the Z-axis. So it goes out and backwards. So if you're looking at your paper, X and Y, up and down, left and right, Z goes into your paper and then out at you. Okay? So when we draw in 3 dimensions, we try to express that. So if you're looking at a molecule and we see that the bonds are not just lines, then we know that it's in that Z dimension. So it's either coming out towards you or it's going the opposite direction, like into your paper. So a line means it's in the plane of the paper, and then a different symbol tells you something else is going on. So we have 2 symbols. So let's look at this chlorine here. What's happening with this chlorine? Is he coming forward or is he going back? He's going forward or in front, right? Towards you. It's coming towards you. And then the other one, I know this is not what the question asked you, but the other one tells you what? The dashed one. It's going to the back. It's going back or, I don't know what another word. Going back or behind. That's what it is. It's right there if I could read, right? And then how about our plain old bond right there? What is that one? This is in the plane of the paper or the screen. Right? Because if we have an X and Y axis, that's in the plane. So this one is in the plane of the paper. So you would have like a CL right there. But this one right here, that's the solid triangle, is coming out towards you. And so they draw that as a solid. And the other one, that's the dashed, is going behind. And we just have a really hard time drawing that in paper. So this is how we kind of do it. Okay with that? So let's look at the next one. Let's look at B. It's the same thing. If you're a dashed, you're what? Behind. If you're solid, you're in front. And if you're just the stick, I guess maybe I should do that in red. If you're just the stick, then you are in the plane of the paper. Okay, so for 3.48, we have to determine the shape around the central atom. So when we're trying to draw the shape of the central atom, we have to count how many areas of electron density there are. What is an example of something that is an area of electron density? What does that mean? So one area of electron density, what could that be? One single bond. What else could it be? One double bond. What else could it be? One triple bond. What else could it be? I'll give you a hint. It's on the molecule in A. A lone pair, one lone pair. The single, the double, and the triple all take up about the same amount of space. And you got to remember that electrons are all negatively charged. So, you know, opposite charges attract, like charges what? Repel. It's like what I was talking about with your siblings, right? You repel, I repel with my sibling, you know. Not on the big stuff, but you know, when we had to live together, that was a problem. So we repelled, right? So the electron pairs want to repel from the other electron pairs. And it's all equal in terms of bonds. But when we get down here to this lone pair is only shared by one atom. And so it kind of like spreads out. Those two electrons are oppositely charged in that lone pair, and they want to get as far away from each other as possible. So they kind of spread out. But anything in a bond is shared by two atoms. And so they're constrained by where they can go because they have to be between the two atoms. They can't get out of place. Otherwise, they're not in the bond. But those lone pairs, oh, they just relax and spread out, right? So the lone pair takes up more room than a bonded. Let me see if I can read the chat so I can talk, so I can write bonded, B-O-N-D, bonded pair. So when we talk about molecular shape, that's going to make a difference, right? They all want to get away from each other as much as possible. So all those bonds and all those lone pairs are going to arrange themselves to where they can get as far apart as possible. So I want to first do B. How would I determine the shape of B? I need to count my areas of electron density. How many areas do I have? 1, 2, 3, 4. I have 4 areas of electron density. So if I have 4 areas, do I have any lone pairs? I have no lone pairs. Not on that central carbon. I'm only talking about that central atom. What's my shape going to be? This one you kind of sort of have to memorize. Tetrahedral. It's tetrahedral. So they're going to arrange so that they are as far apart as possible. So what are my bond angles on a tetrahedral? Like what's the distance between any two bonds in a tetrahedral? 109.5. Now, what happens if I take away one of the bonds and replace it with a lone pair? Look at structure in A. What's the difference between the arrangement around the central atom in A versus B? I still have 1, 2, 3, 4 areas of electron density, but this fourth area is a lone pair. So I like to draw it as a big bubble so that I know that it takes up space. So what's going to happen to all those other bonds? They're going to get pushed down. So the bond angle is going to change for A. Whoa. Right? So for A, I'm going to have something that is less than 109.5. So we're going to call it something different because it has a different bond angle. So what do we call this one? Pyramidal. Because when we look at the molecule, it kind of looks like a pyramid, right? The 3 atoms are at the bottom and they come up to the nitrogen, and the nitrogen is like the peak of the pyramid. Okay. Let's see, so what's next? Oh, we gotta go to another page. All right. And I just realized this in the last class, I didn't do B. I like completely skipped over B, but that's okay. So determine the shape around the orange colored atom or atoms in each of the following structures. So let's look at this first carbon right here. How many bonded areas do we have? How many, I'm sorry, areas of electron density, not just bonded, but any areas. 1, 2, 3 areas. So I'm going to have more room in this molecule between my electron pairs than I did in the one with 4 areas, right? It's like you got rid of a sibling, so you got a whole nother area to space out in at your house, right? I only have 1 sibling, but that was plenty enough. Okay, so what's my bond angle here? It was 109 before. Is it going to go up or down? It's going to go up to 120, right? Now I have more space between my bonds. So what's the name of this structure? Trigonal planar. And we call it trigonal planar because all the atoms are in the same plane. How about my next carbon? This carbon right here. How many areas of electron density do I have? 1, 2 areas. So guess what? I got rid of another sibling. I got more room in the house. So look at my bond angle now. If it was 120 before, is it going to go up or down? It's going to go up because I have more space. So this becomes 180 degrees. If you have something that's 180 degrees, that's a straight line. So we call that linear. Okay. All right, same thing on this one. So in A, let's do the carbon first. Let's do the carbon first. How many areas? 4 areas around the carbon. So what shape is that? Tetrahedral. What's your bond angle? 109.5. Now let's look at our oxygen. Here's our oxygen. How many areas of electron density? 1, 2, and then 3, 4. So when you think about this one, I kind of want you to think about oxygen bound to two things, any two things. And the one that comes to my mind most easily is water. So I have oxygen bound to two hydrogens, and you end up with two lone pairs. Have you seen water drawn like this before, where those hydrogens are kind of down low and they're close together? Why? They have these big areas of electron density, and so they push those two hydrogen bonds, or whatever the oxygen is bound to, down together. So we went from, where did we go? Hold on, I want to show you. From right here, we have 3 bonds and 1 lone pair. That was pyramidal, so we said that's less than 109.5. Well, if we get rid of another bond and turn it into a lone pair, that's what we are here. So before we said it was less than 109.5, so this is less than 109.5. It's really 104, but you don't have to know that. You just have to know that the bond angle is getting smaller and smaller the more lone pairs we have. Okay, and so what shape do we call that? Bent. And you can see those bond angles are pushing together, and so you end up with kind of like almost a bent structure. So it looks kind of like that. Okay, our last one. How many areas around that first carbon? 1, 2, 3. How many areas around the second carbon? 1, 2, 3. Any lone pairs? So both carbons are what? Trigonal planar for a degree angle of 120. All right. I think there's only one problem in the next section. Super easy. We got a little bit left. Okay, so we're going to talk electronegativity and molecular polarity. Now, I was really bad and I did not provide you with your electronegativity table. So if you have your book, y'all help me out and go to your table on electronegativity values. Let's see. Here, page 111. That's where I'm pulling these numbers from. Okay, so page 111, if you want to see your table. So I'll write that down. Page 111. Okay. So for each of the molecules, we're going to draw a Lewis structure. We're going to label polar covalent bonds with our dipole moment, and we're going to determine if the molecule is polar or nonpolar. So when we talk about molecules being polar or nonpolar, polar tells us if we have a partial charge or not. So the more time an electron spends around an atom, the more partially charged it becomes. And it becomes partially negatively charged. What did I say was the most electronegative element? Fluorine the floozy, right? She will take electrons from anyone, right? But it's easy to remember. I've never forgotten that, right? I hope you never forget that. Fluorine the floozy. So when we look at this, in order to determine the polarity of a molecule, we first have to look at the bonds, then add up all the polarity of the bonds in order to find out the polarity of the molecule. So let's do the first one, CH3Br. What is my electronegativity for carbon? Go look on your table. These are your electronegativity values, E negativity values. Page 111, table or figure 3.14. Okay, so carbon's 2.5. Hydrogen, what's hydrogen? 2.1, and bromine 2.8. The book tells us that carbon and hydrogen, their electronegativity values are so close that we assume they're the same. Depends on what book you read, what they say. But for this class, we're going to say that they're basically the same. basically equal. Okay, so we're going to assume there's no electronegativity difference between carbon and bromine. So if we put carbon as our central atom, and we put 3 hydrogens around it, we know each hydrogen has 1 electron, each carbon has 4, and then we put a bromine. Bromine has 1, 2, 3, 4, 5, 6, 7. To give everybody a complete octet, we're going to make some bonds and then evaluate. We got to connect everybody first. And it looks like by doing that, hydrogen has its duet and everybody else has its octet, so that's good. So look at bromine. Bromine and carbon have an electronegativity difference. Which one is more electronegative? Which one is hogging those electrons? Bromine. So you're going to make an arrow to indicate the polarity of that bond between carbon and bromine. And we're going to point at the negative bromine, and we're going to put a plus sign on the end by carbon because carbon is partially positive. Because that electron is not spending as much time with the carbon atom as it normally would. And so we end up with a slightly positive charge. How about our bonds between carbon and hydrogen? Are they polar? Do we have a negative and a positive? Nope. Because we just said that although they do have a difference, they're basically equal. So we basically say that those are non-polar bonds. So carbon, hydrogen are non-polar bonds. Now I want to draw an overall molecule polarity. I've checked all my bonds. Now I need a molecule polarity. How should I draw my arrow? Towards my bromine, right? So it should kind of go like that. So it's just one big arrow that's about the length of your molecule, and you point towards the negative part of your molecule. Okay, how about HF? Hydrogen's got 1 atom, 1 electron. Fluorine has 7. To complete fluorine's octet and hydrogen's duet, all we need is 1 bond. So do we have an electronegativity difference? We got fluorine the floozy, man. She is 2.0, she's 4.0, and hydrogen is 2.1. That's a big electronegativity difference. So who are we going to point at in our bond? Point at fluorine, put our plus sign by hydrogen. That's our bond polarity. What's my molecule polarity? How many bonds do I have in my molecule? Only 1. So my molecule polarity is going to be the same. How do I keep doing that? I think it's my watch. Okay. So my molecule polarity is the same as my bond polarity if I only have 1. Okay. And I know class is officially over. I'm going to do C and D if anybody wants to stick around and see it. But y'all are welcome to go. So PBr3, just so that we have them all done. So phosphorus, valence electrons, how many? 5, 1, 2, 3, 4, 5. Bromine has 7. Y'all are really free to go. It's okay. But if you want to stay, you can. Okay, putting them all around bromine. Now I'm going to make my bonds. So I'm going to bond. I'm going to bond, and I'm going to bond. And that gives me a complete octet, so I'm happy. So I need to look. Phosphorus has an electronegativity of 2.1. Bromine has 2.8. So here's my more electronegative atom. I'm going to point towards my more electronegative atom. Point. Point. But what's the problem with this? There's one problem with this. Are we thinking in 3 dimensions? No, we're not really thinking in 3 dimensions. This is really taking up a lot of space. So really what you have are basically this, right? With your lone pair on top. And it's just pushing those bonds down. And so if you have bond polarities that are pointing towards our negative bromine, right? Our overall is going to be basically that. Okay, let's see. What's our last one? OF2. I'm trying to scroll up, but OF2. So oxygen has how many? 6, right? Fluorine, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. We're going to make our bond. Make our bond. What does this resemble? H2O, right? We're just putting it OH2. I mean, it doesn't matter. So what your actual shape is going to be is that bent structure, right? Where you have fluorines coming down this way. So you're going to point towards your more electronegative fluorine. You know fluorine's a floozy. You don't even have to go look on the chart. Fluorine's a floozy. She just is. So your overall polarity of your molecule is going to be the combination of those two. It's like a vector. If y'all have ever done physics, it's like a vector. All right, that's it. Don't forget, homework's due on Monday at 9 p.m. And if y'all need anything, let me know. Oh. They're polar. They're all polar. They're all polar. Thank you. Right? They're all polar. Does it say label each bond, determine the molecule? Yeah, you depend. Well, if you draw a dipole moment, by definition, they're polar. So, but that's great. Yes, they are all polar. If you had something like CH4, right? No polar bonds, it would be a nonpolar molecule. Or if you had something like CF4, they're all polar bonds, but they're a symmetric molecule. So that would also be nonpolar. But in this case, they were all polar. Anybody else got questions? Good? So dipole, so like water, right? Here we were showing water or whatever it is. So if you have a dipole, what it's saying is that if I had, let me come down, let me extend the page and I'll show you, right? So if I had water, and this is my dipole, right? I have a positive side down here and a negative side down here. If I have another water molecule, and I do this again, right? This portion is slightly positive, this portion is slightly negative. So it's the dipole of one interacting with the dipole of another, and that's a dipole-dipole interaction. Dipole-dipole. So dipole-dipole requires 2 molecules. A dipole is only 1 molecule. That's why it's said twice. Good? All right. I'm gonna end the Zoom.